My name is Chris Hickson, and this is the study guide for probability for fourth and sixth period. And so let's go ahead and jump right in. We have a lot to get to. So the first thing we're going to talk about is determining the likelihood of each event. So when we did this, this was one of the first things we talked about in probability. There were several terms we talked about, and they were impossible, unlikely, as likely, as not, which we called Allen, likely, and certain. So we're going to be using those to answer these. So the first one is 0.48. And so what we're doing is just seeing whether or not it's halfway, because if you recall, if we had our little graph here, this halfway point was as likely as not. Greater than half was considered to be likely. Less than half, whoa! Sorry about that. Less than half was considered to be unlikely. At exactly 100% or 1 was considered to be certain. And at exactly 0 was impossible. So now let's look at these. 0.48 is a little bit less than half. Remember, at a half, we've got 0, 1, and 0.5. 0.48 is a little less than half. So this is unlikely. 0.5001 is slightly larger than half. So this is likely. 1.0 is certain. 0.001 is unlikely. 15% we can change to a decimal is 0.15, which is unlikely. 50% we can convert to a decimal, or 50.001 rather. Oop, I actually did it the wrong way. I did this wrong way too. This should be this way. And let's erase this. Sorry about that. There we go. And that's going to be 0.50001, which is a little tiny bit bigger than 0.50, so that makes this one likely. 0.1%, again, we can convert this to a decimal, which is 0.001, which is unlikely. 100% is certain. Number 9, I had some fractions, so let me pull those up for us real quick. The first fraction was 4/10. And we can divide this out. So I'm going to go down here and erase some of this stuff. Now, 4/10, we can take 4 and divide it by 10. 10 does not go into 4. And in order to add a 0, we have to put a decimal there. And then 10 goes into 40 4 times. 4 times 10 is 40. So that's our answer, 0.4. 0.4 is less than half. So we know that 4/10 is going to be unlikely. The next one is 3/6. And again, we can either divide this, but some of you might have noticed that 3/6 is exactly 1/2. Because if you take 3/6 and you divide both of these by 3, you'll get 1/2, which we know is 50%, or Allen. Oops. But we can still divide this out. So 3 divided by 6. 6 does not go into 3. Again, we add a decimal. Oh, we're not going to do that. Get a 0 here. 6 goes into 30 5 times. 5 times 6 is 30. So our answer is 0.5, which we know is as likely as not. Is that for number 10? Yeah, cool. So 3/6 is Allen. For number 11, we have 0 out of 134. 0 divided by 134 is just 0, so this is impossible. And 12 says 5/6. So again, we can divide this out. 6 does not go into 5. So we add a decimal, add a decimal. 6 goes into 50 8 times. 8 times 6 is 48. 2. We add another 0 and bring it down. 6 goes into 20 3 times, and this is going to repeat. So we're going to go ahead and leave it here. So we'll get 0.833. Which is greater than half. And most of you might have noticed that this fraction 5/6 is also bigger than 1/2. So because of that, you'll note that number 12, 5/6 is a likely probability. Alright, that's the end of that one, so let's go ahead and jump to the next section, which is probability. Number 13 asks of drawing a club from a standard deck of cards. So we know that a standard deck of cards has 4 suits. Ooh. So they have 4 suits. They have hearts, spades, diamonds, and clubs. Let's see if I can do this. So there are 4 different suits, 4 different possible outcomes. And we know that we're talking about drawing a club, so that's one of those possible outcomes. So we have a probability of 1/4. We could divide this if we want to. We don't have to. This can be our answer. But if we want to, we can divide this out. 1 divided by 4. 4 doesn't go into 1. 4 goes into 10 2 times. 2 times 4 is 8. So left with 2. Add another 0 and bring it down. 4 goes into 20 5 times. And 5 times 4 is 20. And so we have 0.25. If you wanted to, you could even convert that into a percentage, but again, you don't have to. 0.25 converted to a percent is 25%. I will accept any of these answers. Alright, the next one. In a jar full of marbles, there are 4 green, 6 blue, 8 purple, and 12 orange. Probability can be given in any form, percent, decimal, or simplified fraction. So we're just going to do simplified fraction because honestly that's the easiest one. If you would like to convert to a decimal doing it this way or a percentage doing it that way, it's totally up to you. So the first thing we need is the total number. And the total number is going to be 4 plus 6 plus 8 plus 12. Alright, we've got 4 green, 6 blue, 8 purple, and 12 orange. So this is going to total to 30. So we know that this is our denominator. So now we're going to take the probability of green, this guy right here, and put it over 30. Now we need to simplify this. I can divide both of these by 2. I know that I can do that for sure because they're both even numbers. 4 divided by 2 is 2. 30 divided by 2 is 15. And there's my probability. Now let's look at blue. Again, we're going to be over 30 because it's the same total each time. I'll go ahead and select the blue color. And it says we have 6 blue. And I know that I can divide 3 into both of these. I can probably divide something larger, but let's just start with the small number. 6 divided by 3 is 2. 30 divided by 3 is 10. Oh, look, they're both even, so that means, or still even rather, that means we can divide by 2 again, or divide by 2 rather. 2 divided by 2 is 1. 10 divided by 2 is 5. Probability is 1/5. Now let's look at purple. So we've got 8 purple marbles, and again, we have the same fraction here, the 8 over 30, or the same denominator. That's still our total. And these are both even, so let's go ahead and start with dividing these by 2. 8 divided by 2 is 4. 30 divided by 2 is 15. And there are no numbers that go into either of these, so we're done there. And now orange. It says we've got 12 orange. So we'll set up our fraction as 12 over 30. And they're both even, so we can start by dividing by 2. If you see a larger number, that's totally okay. So we'll be at 6 over 15. Nothing goes into 6 and into 15. I totally lied to you. 3 goes into both 6 and 15. Sorry, everyone. 6 divided by 3 is 2. And 15 divided by 3 is 5. Alright, the next question is the probability of getting a black marble. Well, if you notice, we don't have any black marbles. So we're still out of 30 because there are 30 total marbles in there. And we're talking about the probability of drawing a black marble, which there are none in there, so there are none that we can draw in there. So that is our fraction, or 0%. That's the end of that one. Alright, take a moment to pause, and we're going to move on to unbiased versus biased. Okay, number 19 says, if you need to find out whether people in Tucson like chocolate or vanilla ice cream better, which of the following sampling methods would give unbiased results? So the keyword here, oh man, I do this every time, team. The keyword here is unbiased. So remember that unbiased means fair. So go to circle 1. Asking your neighbors, randomly selecting a few ice cream shops in town and asking people as they come in, asking your friends, and asking your classmates. Well, if you remember, it was unfair to ask your friends, so we can go ahead and get rid of that one. It's definitely not this. Asking your classmates is kind of the same thing. We're talking about trying to find things in Tucson. Trying to find out whether people in Tucson. So remember, people in Tucson, this is going to be our population. So we need to figure out which one of these best matches the population we're talking about. And asking our classmates isn't a good representation of people in Tucson. Again, asking your neighbors, that's only asking a couple people. That's not very many people. So get rid of that. I'm left with B. And randomly selecting a few ice cream shops in town is nice. And then asking the people that come in is a good way to find that information. Alright, let's move on to number 20 and 21. A survey was conducted last month. The University of Arizona wanted to know how many of their students, so it's talking about University of Arizona students, how many of their students use the bus for transportation. In order to find out, the U of A asked 349 students, randomly selected in the student union. Okay, cool. So the first thing is to identify the population. Remember, the population is who we're talking about. So in this case, it's talking about the University of Arizona students. That's who they're asking. And the sample is the number of people they asked. And here we found out they asked 349 students. Well, that's it. Population and sample identification is as easy as that. Alright, that's the end of this section. So go ahead and finish up and we'll move on to sample spaces. Okay, sample spaces. Determine the sample space of the following. A deck of 52 cards. A deck of cards has 52 cards. You should already know that. We talked about that. If there are 4 suits, we also already know that. If there are 4 suits, and you want to determine the likelihood of drawing a certain suit. So a certain suit tells me it's one suit that we're after. What is your sample space? Well, I know that there are 4. Oh, I'm sorry. It's asking what our sample space is. I was over here trying to figure out the probability. So this actually is not going to matter. So it's asking us our sample space. Well, we're looking at suits. So our sample space is going to be made up of all the different suits. So we have hearts, clubs, spades, and diamonds. And that's it. That is our sample space. Now, in a jar full of marbles, there are 4 green, 6 blue, 8 purple, and 12 orange. So this is the same problem we had before. And it's asking us this time to only identify the sample space. So we can do that. There are green marbles. There are blue marbles. There are purple marbles. And there are orange marbles. And that's it for our sample space. And that is it for sample space. So finish up and we'll head on to FCP. Alright, we're going to use the fundamental counting principle to determine these. We also have to draw a graph of some sort. We'll use a diagram. So determine the number of combinations of flipping 2 coins. So I think it's literally been every time I switch. Alright, so we've got 2 coins. And each one of these coins could be heads or tails. So each one of them has 2 total options. So we know that if this has 2 options and this has 2 options, the fundamental counting principle says that we can do 2 times 2 is 4, and this is the number of combinations. Now we can use a diagram to show that. We have each coin, and each coin has, I'm sorry, let me back that up. We can use a diagram because we can flip the first coin. First coin, and it can be either be heads or tails. And then we get the second coin. And it can either be heads or tails. So if you notice, one of our options is going, the first coin being heads, the second being heads. The first coin being heads and the second coin being tails. The first coin being tails and the second coin being heads. The first coin being tails and the second coin being tails. There are 4 different combinations. Alright, let's move on to 25. Determine the number of combinations of rolling 2 dice. So this is going to work out the same way, where we know that each of our dice have 6 different options for what they could be. And so the FCP says that we can do 6 times 6 is 36 combinations. And we can use a diagram to show this. This gets a little crazy, but we have our first dice, and we can get a 1, 2, 3, 4, 5, or a 6. And this will go to the second dice. And each one of these will have a 1, a 2, 3, 4, 5, 6. You'll do the same thing for all of these ones. You'll actually need to draw them out, but you'll have 36 different options. If Chris owns 4 shirts, well, actually I do this. 4 shirts, 2 pairs of pants, and 2 pairs of shoes, how many possible outfit combinations does Chris have? So let me move this down so that way, or move it up rather, so it's not in front of the camera. Sorry about that. Actually, I might need to move it down. Not put my camera on bottom. That's okay. Sorry. Anyway, so we've got 4 shirts. Our fundamental counting principle says that we can do 4 shirts times 2 pairs of pants times 2 pairs of shoes. 2 times 2 is 4. 4 times 4 is 16. So there are 16 outfit combinations. And we can set that up. We can have our 4 different shirts. I'm actually not even going to try to draw that. No one wants to see that. We'll call them shirts. We'll call them S for shirts. So 1, 2, 3, 4. And he has 2 pairs of pants for each one of them. Pants 1 and pants 2. We'll call this shirt 1, shirt 2, shirt 3, and shirt 4. Pants 1, pants 2, pants 1, pants 2, pants 1, pants 2. Each one of the pants has access to 2 different shoes. Shoe 1, shoe 2, 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 onward and onward. And so if you count each of these up, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 combinations. And that is the end of your study guide. If you have any questions, please let either Addie or myself know. Your test is on Thursday, so that'll be tomorrow by the time you've seen this. So make sure you get studying. Take care, 4th and 6th period, and good luck.